Hello, in this video we're going to continue with our study of geostationary satellite orbits, and in this particular video we're going to look at artificial satellites that are placed in geostationary orbit about our moon, the moon. So the question here is, how high above the surface of the moon does a geostationary satellite need to be to always remain over the same point on the moon's surface? And by the way, that's what defines a geostationary satellite. It's the fact that it remains over the same point on a planet's surface all the time, whatever that planet is or moon. A geostationary satellite always remains over the same point at all times. So anyway, we're given some information here because we want to find the distance of the satellite from the centre of the moon first. And we're given some data. The radius of the moon is 1,738 kilometres. But this equates to 1,738,000 metres. Now, the mass of the moon is 7.348 times 10 to the 22 kilograms, and the gravitational constant is 6.672 times 10 to the minus 11 Newton meters squared per kilogram squared. And the time that the moon takes to revolve about its own axis is exactly the same as the time it takes to go around Earth, because it's tidally locked. So that's how we know that. So the time that the moon takes to revolve about its own axis is actually 27 days approximately, which is 2.3328 times 10 to the 6 seconds. Now let's make a start, because some of the working is similar to that of the last video. And if I draw a picture, this might help us work out some of the expressions and the mathematics that we need to model this. So we draw a circle here, and that's supposed to be the orbit of a satellite of mass m travelling at velocity v, and the moon, whose mass we assume is all concentrated at its very centre, is m. And I think we'll call that m sub m. Like we should have called it above. So I'm just going to check that for consistency. Yes. Now, let's just change colour, because the radius of the satellite's orbit from the centre of the moon is capital R. It's much bigger than the moon's own radius, and we'll draw the moon's radius in as well. But if you imagine that that is the moon, it's not a perfect circle, but anyway, that would be the moon's radius. We'll call that Rm. Right, and the satellite, between the satellite and the moon, is a force acting downwards, which we'll call F. Now, F has two components. Because we're talking about a satellite in orbit, we can't assume that it's on the surface of the moon. So we have to use this expression, F equals mv squared over r. So that would be equation 1. And there is another force as well due to the gravitational constant, and that is G big M sub m little m over r squared. And that is equation 2. Now, because this system is a geostationary system, that is, the satellite is in a geostationary position above the moon as it travels around it, we can equate equations 1 and 2. So that's what we're going to do. Let's go and write this down then. So we've got mv squared over r, big R, equals g m little m over r squared. And I'm going to use up this bit of space here. This implies that, well, as you can see, on both sides of that equation, we've got a small letter m representing the satellite's mass. So that cancels with that, and one of the r's cancels with one of the r's on that side. So we're left with v squared equals g m over r, and that's m sub m, by the way, and we'll call that equation 3. Right? So what we need to know now is, well, we don't explicitly know what this v is, this velocity of the satellite, but we can work out an expression for it. If we knew the velocity of the satellite to begin with, given that we know big G and big M sub m, then we could easily work out the radius, but we don't know v. So what we can surmise is that because we're talking about a geostationary orbit, and I'll write this down, geostationary orbits are usually circular, meaning that the distance a satellite travels in one revolution is the same as, just let me make that look a little bit neater, then you can read it. It's the same as that orbit's circumference. Right, so geostationary orbits are circular, meaning that the distance a satellite travels in one revolution is the same as that orbit's circumference. Should be an apostrophe there. So what is the circumference of the orbit? Well, the circumference is equal to 2 pi big R. This means that the velocity must be the circumference, which is just a length basically, divided by the period or the time that it takes to complete one revolution. So that's equal to 2 pi r over t. and we'll call that equation, let me see, we'll call that equation 4. So that is equation 4, right? Now, we've already got an expression for the velocity, and that's in equation 3, which is v squared equals g big M sub m over r. If we substitute this into v squared equals g big M sub m over r, we get, and I'll write this down, substituting equation 4 into equation 3, we get and I'll just scroll down a little bit. We get 2 pi r over t all squared, and that's equal to g big M sub m over r. So what we can do now is square everything on the left hand side so that we get 4 pi squared r squared over t squared, and that's equal to g big M little m, the mass of the moon, over r. Now, we're nearly at a quite important result actually, which I'll explain in a moment, but if we multiply both sides of, I think this should be equation 5, shouldn't it, above? Yeah. Multiply both sides of equation 5 by r and t squared. I can't quite get that on there, it's a bit messed up, isn't it? So r, I'll put the t squared there, by r and t squared, and divide both sides by 4 pi squared, we get r cubed equals g big M little m t squared over 4 pi squared. Let me check that I've copied that partially down correctly. Yeah. So we'll call this equation 6. Right? Now, what is equation 6? Well, equation 6 is Kepler's third law. Equation 6 is Kepler's third law. And there are various forms of this. You know, you might see it written as r cubed, or the cube of the distances are proportional to the squares of the periods, and quite often it's pronounced as the square of the periods, or the square of the period is proportional to the cube of the distances between whatever the satellite is and the planetary body, or the moon, or whatever, you know. And what you will also find is that, because you don't generally want a proportionality sign in here, you often get these written as r cubed equals k1 t squared, and that will be t squared equals k2 r cubed. And of course k1 would just be equal to g big M sub m in this case, divided by 4 pi squared, and k2 is just the reciprocal of that, so it's 4 pi squared over g big M sub m. And that's all that is. So it's Kepler's third law. Now, it should be fairly plain sailing to work out what r cubed actually is. So I'm going to copy this. I don't think the r cubed bit will be copied, but we'll go on to a new page because I want to be able to see that equation when I copy the values into it. So we've got r cubed is equal to that. So therefore, substituting in values, we get r cubed is equal to g, which is 6.672 times 10 to the minus 11, times the mass of the moon, which is, we have to scroll up for this again. Let's just scroll up. 7.348 times 10 to the 22, and I haven't left enough space on there for myself, so let's just cut and let's just, there we are. I think I'll just erase that and push everything up to the left hand side a bit more. Sometimes I do this, so many apologies. So r cubed is equal to 6.672 times 10 to the minus 11 times 7.3, did I say 348? I have to have a look again. I should have these figures written down. Yeah, 7.348 times 10 to the 22 times 10 to the 22 times t squared. And what is t? Well, it's 2.3328. Remember that, 3328. .3328 times 10 to the 6, and that is squared. I've forgotten again. My memory, as I said in the last video, is not very good, so I forget everything. The minute I think of something else, it goes. Let's just make that bracket look a little more like a bracket. There we are. So there we are, and that's divided by 4 pi squared. Now I'm going to have to work this out on my calculator, so you'll have to bear with me, but I'll read it out as I'm doing it. So we've got 6.672 times 10 to the minus 11 times 7.348 times 10 to the power 22 times, in brackets, 2.3328 times 10 to the power 6, close bracket, and then square that term. And what do we get? We get r cubed is equal to 2.6679. Well, we'll do it to 1, 2, 3, 6 significant figures there, times 10 to the 25, and that's divided by 4 pi squared. Right, so we'll just scroll up a little bit, and we'll divide that out by 4 pi squared, and I get, do check my figures because I do make mistakes, so r cubed is equal to 6.758 04, we'll call it 1, 2, and that's 6 significant figures again, times 10 to the 23. Now it's quite simple to find the radius of the orbit of the satellite from the center of the moon. We take the cube root of both sides, like I showed in the previous video. I'll just do it again for your benefit if you haven't seen the previous video. So that's equal to basically 6.67 or the one of the 6.6 6.75804 times 10 to the 23, all to the power of 1/3. So let us find out what that is. So if we do 6.75804 times 10 to the 23 to the power of 1 divided by 3 in the indicial part, we get, wait for it, there should be a drum roll here to coincide with me scrolling up and down all the time. So anyway, we find that r is equal to, and that's what r was equal to as well. R is equal to 87, I think it is, 87,355,326.68 meters. Now I'm going to double check something because yeah, that's right, we didn't actually in the end need the radius of the moon, I don't think. But anyway, so what's that in kilometers? So the radius of a geostationary satellite is above the center of the moon is 87,755.33 kilometers. God, that seems high. That's really high. I hope I haven't made a mistake. I'll just absolutely double check that. To the power 1 divided by 3 divided by 1,000 is 87,755 kilometers. Yeah, so that must be the answer. Now, we didn't use the radius of the moon in that, I don't think, if I remember correctly. But we need to use the radius of the moon now because we need to answer the question. The radius of the moon is 1,000, I've done it again, 1,738,000 meters. 1738. So, how high? Let me just go back. So the radius of the moon, now why is, there we are. The radius of the moon is 1,000, let's just get rid of that little decimal point, 1,738, 1,738,000 meters. Or if you like, RM equals 1738 kilometers. So how much higher than the moon does the satellite need to be? Well, it needs to be, thus the height of the satellite above the moon's surface needs to be, and I just have to, oh yeah, there we are, needs to be, well, we'll just call it lowercase h, 87755.32668. I don't really need to do it to that level of accuracy, but I have anyway. So what did I say the radius of the moon was? 1738. And so if we subtract that, we get a height of 86,017.33 kilometers. And that is the answer. Okay, so again, just to recap, we wanted to find the geostationary height above the surface of the moon, given this information here, and we've substituted it into what effectively becomes Kepler's third law in equation 6, and worked out the radius cubed, and then we've taken the cube root as shown here to get a radius of the orbit of the satellite above the moon's centre of 87,755.33 kilometres, meaning if you take the moon's radius of 1,738 kilometres into consideration, that the height of the satellite above the moon's surface is 86,017.33 kilometres. So I hope that's been helpful. I might come back with another one for Mars or some other planet. So we shall see. So until then, I remind you to do by all means look at my other videos, of which there are a growing number now. And until the next time, I'll bid you farewell. So goodbye for now. Okay, bye.